So now let's talk a little bit about how we're going to do some specific modeling and some specific problem solving with free fall. So the first thing is that we're going to say that our acceleration in the y direction is equal to minus g. Now again, we can say this because g itself is going to be 9.8 or 9.80 meters per second squared, and g is positive. So this is the first thing. Be really careful about this, because if you also call g negative, then you'll think that this minus sign cancels, and it doesn't. So please keep the minus sign explicitly out front. So the first thing is to just think of a simple motion diagram that in this case represents an object starting at this height, starting from rest, and it has an acceleration downwards. And this acceleration downwards is constant. Again, this is the idea of free fall, that the acceleration is in the y direction. So typically the coordinate system we would use is x to the right and y up. So if the positive y direction is up and our acceleration is down, that's why we need this minus sign here. The other thing to keep in mind is that gravity never pulls you sideways. Gravity always pulls you straight down, and that's why we get to say that this is in the y direction. So that's the pictorial representation. We can then create a plot of velocity versus time for this situation, and again it was starting at a time of 0 at a speed or velocity of 0. Now again, notice that all of our velocities are negative here, and that tells you that it's traveling downwards. It's traveling in the downwards direction because negative, right? Up is positive. So now the other thing to remember is that our acceleration is going to be equal to the derivative, and in this case I'm going to say specifically the y direction, right? This is dv dt, where both our velocity and our acceleration are in the y direction. So we have derivatives here. And you can see that this has a constant slope, so our acceleration is constant, and it's negative. Our slope here is negative. So that's how all of this is consistent. The picture, the plot, the equations, and this specifically for free fall is the idea that our acceleration is equal to negative g. Now something to be careful here is that if you wanted to draw a plot of position versus time, remember that we would need to integrate the, and this would be y in meters. We would need to integrate this. So now note here that your integral here is all negative, right? So the integral dt is less than 0. So you have a few choices. One choice would be to set this initial position here as 0, and then your position would be always negative. Another option would be that we could say that, for instance, this position here is y equals 0, and this is some initial y value. And so if we have an initial y value here, what this looks like is a parabola that's concave down, and that is, of course, decreasing towards 0. So I'm not great at drawing a parabola, but it would look something like that. So this is what free fall position will look like. Now one thing to be careful about is that you're going to see similar shapes when we get to projectile motion, but those will be plots of y versus x rather than y versus t. So remember that, again, concave down because our acceleration itself is negative, and you can get this by just doing the integral. So that's what our free fall is looking like. Again, we're using our constant acceleration model where our acceleration is equal to negative g. So briefly, I want to talk you through an example in the book where instead of giving you a plot, there's again a motion diagram, which again is an object that's being dropped. So really all of these motion diagrams are going to look pretty similar. And in this case, you have this nice sketch. Now, one thing that's important about doing a sketch like this is that you're clearly defining where y equals 0. Y does not equal 0 at the beginning, y equals 0 at the ground, at the end point. And so we have an initial height here, which is our initial value of y, and our object is being dropped from rest, so our initial speed is 0. Now, one thing to note in this problem, and again, this is coming from the book, but I want to highlight this, is that we can say that our clock starts when we drop it, which is fine. Our initial time equals 0 seconds. But one thing that you don't actually know in this problem is what the time is when it hits the ground. So one thing that you'll see frequently are situations like this in constant acceleration and free fall, where you don't actually know the time that something is happening. But in this case, what you're trying to find in this problem is what the speed is when it hits the ground. Now, one thing I want to say is that frequently you would be drawing this motion diagram, this picture, and making this table. The problem might simply be, you drop a rock from 20 meters up, what is the speed when it hits the ground? That's what you would be given, and you would actually need to generate this. Now, you don't actually need this. Now, it's true that at some time it's hitting the ground. Now, you should write that here, but you don't actually need to find it. So you should think through this case, how can you model this? Now, one option would be to find the time that it hits the ground, and then to find the speed that it would have, given that you would know then the amount of time that it was accelerating over. But there's actually a different approach. When we talked about constant acceleration, I called this the time-free kinematics equation. And it had both our final velocity, our initial velocity, the acceleration, and the displacement, or change in position, but it did not include time. So this is actually the most straightforward way to do a problem like this. That in this case, we have our initial velocity is going to, in the notation that this problem uses, is equal to 0 meters per second, and the final here is using the notation of v1y, and that's what you're trying to find. This is what you're solving for. So now our ay, we've said for free fall that this is equal to negative g, and remember that this delta y is y final, which in this case is y1, minus y initial. So now, one thing that I would always recommend doing in a situation like this is to rearrange for what you're solving for and then actually plug in numbers. So since you already have what you're solving for by itself on the left, all you really need to do is take the square root. So in this case, I'm just rewriting the equation with the notation used in this problem, but I'm going to take a square root of the left side. And I have that this is going to equal the initial final squared plus 2. And I'm always really careful here that I'm plugging in negative g for a sub y, and I'm literally going to show that that's what I've plugged in. And I'm also going to explicitly put in y1 minus y0 to be really careful about my signs. So now remember that because I'm taking a square root of the left, I need to take a square root of the entire right side. Okay, so now I have v1y, and since this was equal to 0, I'm actually going to drop that term. So I now have, and this is where you have to be careful, I have 2 times negative g, which since this is on Earth is negative 9.8 meters per second squared. But now be really, really careful about this, in that your y1 is equal to 0, and your y initial is equal to 20 meters. But note that it's 0 minus 20 meters, so this is negative 20 meters. And part of why this is so important is that a mistake that students make very frequently is that they either switch the order here so that you don't have a minus sign, or they drop the minus from the g. And so here you see that you have 2 times a negative number times a negative number. So that becomes a positive number, which is good because you're taking the square root. If you take the square root of a negative number, you get an imaginary number. velocities can't be imaginary. So what that means is that you've made a mistake. Anytime that you're doing work in physics class and you take the square root of a negative number to get some sort of physical quantity, you've made a mistake. So please be careful, and especially in this case, if you have a sign mistake, it will show up here. So you have a minus sign from your acceleration and you have a minus sign from your change in position, because your change in y was going down. And remember, we say that our positive y direction is up. So be very careful about that. The other thing that I want to mention here is when you take a square root, remember that you can get a positive or a negative value. And so since it's heading downwards, whatever you get should actually be a negative value. So this is going to give you the speed. You then need to look at the situation to say, hey, that's going downwards. That means it's a negative value. So please be careful about that. So to just briefly summarize, when we're talking about free fall, that means that we're only worried about the acceleration due to gravity. We're not worried about air resistance or really any other forces, which we'll tease out what that means in a few weeks. The acceleration is going to be constant, and we call this both in the y direction and negative, and the value is then g. So g will be a positive constant, and on Earth it's 9.80 meters per second squared. Of course, we use SI units in here, so there should never be feet per second squared. If you've memorized g in other units, you will be needing to use meters per second squared in here.